Okay, so let's continue. Looking at this right here, you are dissolving this amount CaCl2 in this amount of water. So 32 grams of calcium chloride in 271 grams of water. Now our units should be mole for molality is moles over kilograms. Okay. So we go ahead and change it into moles. You find the molar mass, you get 0.288 moles, right? You put molality, which is 0.288 moles divided by your value in kilograms. So you must change this to kilograms. 271 grams must be changed to kilograms, which is 0.271. So your answer is 1.06. You notice that this is a small m. Okay. The small m stands for molal. And molal is the same as if I wrote moles over kilograms. Any questions on this one? Okay. So we're going to do a few more calculations. I have 3 of these here. I want you to try each one on your own. The first one is ppm, which is parts per million. So you're going to take whatever you get as your answer times 10 to the 6. Okay. It is okay to write moles over kilograms. Someone had a question earlier. The calcium chloride is already dissolved in the water. Yes. You don't need to subtract it. It's telling you that this is the mass of the water and this is the mass of the solute. So it's saying this is the mass of the solute, this is the mass of the solvent. If it said this was the mass of the solution of the two combined, then you would need to do some subtraction. So that's actually a very good question. Okay, so once again, go ahead and find out how much calcium you have in this pill. And then the next one is we are looking at alcohol. This is the percent by alcohol by volume. Find out how many liters of alcohol is in that wine. And the last thing is you're given these two pieces. I want you to find the mole fractions of both. Okay, anyone have any questions so far? All right, go ahead and take some time to do that. Okay, Rick, really quickly, help me test the audio. Someone say something.
Professor, can you hear me?
There we go.
Yo.
Okay, I got it. Thank you. So I had to switch the input. Okay, so really quickly, let's go through each one of these. Let's take a look at A here. You have it in milligrams. You want to change that into grams. The reason why is because you want to make sure that they're both the same. So this is grams over grams. This is the mass of your solute over the mass of your solution. So the part over the whole. And since it's parts per million, you times 10 to the 6, you end up with this number right here. I see some of you wrote that number already. Someone else seems to have something off. It could be if you got 10 to the 3 positive, you probably didn't change something along here. Okay, or you missed one of the calculations. I'm assuming you went ahead and flipped the scenario, either a exponent or something.
Wait, can you explain quickly why it's 40 over 0.5 over 3.5 and not the other way around?
Okay, so if we go back to the previous question, right? It says then 3.5 gram pill. So that's our
I
big
get
picture,
it.
right?
I get it.
Okay. All right. So the next one here, the bottle is 0.75 liters. And it says the percentage is 11.5 out of 100. So you simply take that percentage times that, and you get this many liters of alcohol. ppm is parts per million. Okay. Anyone else have any questions before we continue? All right. C is a little bit more complicated. A lot of times they're going to ask you to find just the mole fraction of one thing. And here they want you to find both. My recommendation for you is to always find both. Okay. So you find the moles of each individual thing. The total is always going to be the same. It's whatever your moles are added together. And then it's always a fraction of whatever you're looking at. So this one is the moles of the isopropyl alcohol over the total of the water over the total. So if you look at these two numbers, what happens when you add them together?
You get one.
You get 1, okay? This is always going to be true. All of your mole fractions for everything of your solvents, solutes, all of them added together, your mole fraction totals is always going to equal to 1. I want you to remember that, okay? Anyone have any questions? Okay, let's continue. So we can actually in every case, yes, it's in every case, yes, because each one of the parts added together should equal the whole. So it's the same thing if I took a pie of pizza and I gave everyone a few pieces. If you took all those pieces back together, it should equal the whole pizza. That's what essentially mole fraction is. All right. So interconverting concentration terms, very simply, if you know the moles, right, you can interconvert between the mass and the molar mass because the equation is moles is equal to mass over molar mass. If you know density, you can relate mass and volume because density is equal to mass over volume. So a lot of these can be mixed with one or the other. So you can actually relate your moles directly with your density if you have the volume and the molar mass. So you can start combining a lot of these equations together. And in fact, one of them is the relation between molality and molarity is based off of the difference of density here, because density has mass and volume. Okay. One other thing I want to bring up here, I don't know if I mentioned at the bottom here. The reason why we have molality in addition to molarity, I don't know if it's in the later slide, but I'm going to share it here. The reason why there's why molality exists in addition to molarity is because molality doesn't have volume. So if you look at any of the things that we're dealing with so far, mole fraction is all about moles, right? Moles is really just based on molar mass and mass. If we look at mass percent, it's all about mass. If you look at molality, it's all about mass. But if you look at molarity, it has mass and mass in the form of moles, also volume. Okay. And the reason why we care about that is because molarity is temperature dependent. And the reason why it's temperature dependent is because the volume is temperature dependent. Density is also temperature dependent. It changes because the volume is present. So volume will change based on temperature. It may not change a lot, but it will change based on whatever temperature is present. It can get smaller or bigger. Mass does not change. Mass is always the same no matter where you are. Even if you're on another planet, the mass is still the same. Any questions? Okay. So we're going to go ahead and work on this big question together. It has multiple parts. Before I do that, once again, just to stress, mass, the value of mass does not change. So how many of you have heard of the term law of conservation of mass? Okay, most of you should have, because that's what you learned in Chem 1. Okay, so it's like saying if I had 2 grams of something and I put it in 3 grams of water, in total, there should be 5 grams. And that never changes. But when it comes to volume, volume is temperature dependent and also dependent on the interaction between things. So if I had 100 milliliters of water and 100 milliliters of ethyl alcohol, in other words, ethanol, when I mix those together, it's not always 200 milliliters of the solution. It could be something less depending on how it mixes, or it could be something more depending on how they interact with each other. So I'm going to have you copy down this question real quick. This is not on any other slides. I put this in myself here. We're going to do this on a blank piece of paper afterwards. So go ahead and take some time, copy this down. If you can answer some of this, go ahead and do so. They're looking for the density, the mole fraction of the solvent, not the solute, the molarity of the solution, and the molality of the solution. And I highly recommend looking up the molar mass of H3PO4. Okay, how many of you still need more time? Okay, keep working on it then. Okay, does anyone else still need more time? We'll talk about that in a second. Okay, so let's go through this step by step. So let's just write down information that we have. Okay, if you need a little more time, go ahead and keep working on it. For the time being, I'm just going to go ahead and list out information we have. We have 10 grams of our phosphoric acid. Okay. Does anybody know the molar mass or molecular weight of our phosphoric acid? I always recommend listing down information you have first.
98.
Right, 98, also known as 97.994. So we'll write that down, put that to the side. Okay. I have 100 milliliters of water, right? I assume that's also equal to, we'll assume 1 gram per milliliter for now for density. Okay, so that also equals 100 grams of water. Now, what is the molar mass of water? Should be like 18.02. Okay, so we're going to put that to the side as well. Any questions on this so far?
Yeah, Professor, will it always be 100 grams equal to 100 milliliters?
If they specify that you assume water is normal density, yes. I can tell you this, if it says at 20 degrees Celsius, then yes, it is always 1 gram per milliliter. So you also have to read what they are saying here, okay? In this case, they don't specify it, so you assume that it is 1 gram per milliliter. Any other questions? Okay. So now we're going to go ahead and let's solve for density first. Okay. Really quickly, what I can say is this is 100 grams of water, 10 grams of phosphoric acid. Okay. So if I'm writing down my solution, what is the mass of my solution? (110 grams. Okay. This is your 10 grams of your solutes plus your 10 grams of your plus 100 grams of your solvent. Any questions on this so far? Okay, remember, we're looking for the density of the solution, so I don't care about them individually, I care about them together. The other part that we do have is it tells us that we have 104 milliliters of my solution. Okay, so this gives us a big hint. 110 divided by 104 grams per milliliter. This is my density. So my density should be equal to what? If you enter this to a calculator. I believe it was 1.06 if we were to round it. grams per milliliter. Okay. So that is done. Put that to the side. I'll give you some time to copy this down. Then I'm going to go ahead and erase some of the stuff. Okay. Does anyone else still need time to copy anything? All right. Go ahead and erase this. That is a good tip. Okay. So I'm keeping this information here, right? Now I'm going to go ahead and just calculate the moles of my solute, which is my phosphoric acid. And that's easy. We do 10 divided by 97.994. Tell me what you get. Okay, 0.102. I'm going to just keep that over there. I'm also going to go ahead and find the moles of my solvent, which is my water. So this one is 100 divided by 18.02. This gives us 5.55. Okay. Now I have the 2 moles down. To make things easier, I can go ahead and just do the mole fraction. Okay. It wants the mole fraction of the solvent. So of this substance right here. So a mole fraction, right? Sometimes they refer to it as just an X, capital X. Okay. And since this is of my solvent, you could just write H2O next to it. For the purpose of this, we know this is our solvent, so I'm just going to keep this here, 5.55. It is divided by my total moles. My total moles is just the 2 moles added together. Any questions about this so far? All right. Go ahead and plug this into your calculator and tell me what you get. Okay. 0.982. So this is our mole fraction of our solvent. Now, if you wanted to find the mole fraction of your solute and you already solved for one of these, it's very easy. At this point, you just do 1 minus this number. So then it just becomes 0.11, oh, sorry, 0.018. Okay. And that is the mole fraction of your solute. Because the 2 of these added together should equal 1. Any questions so far? And once again, I'm not looking for this one. I'm looking for this one because that's the question. Okay, does anyone need time to copy this before I erase it? Okay, take that as a no. Oh, let me go back. Okay. So we don't need the mole fraction anymore here. We don't really need the moles of the solvent, but I'm gonna leave that there for now, okay? The next thing is we can look for molality or molarity, either one. We already solved for mole fraction and we already solved for density. The remaining piece, let's go ahead and plug in molarity. So molarity's equation is equal to moles of solute divided by liters of solution. Moles of solute we have, which is just 0.102. And then we know the liters of solution as well, because we can let's go ahead and take the milliliters that we had from before, the 104 milliliters, and change that into liters. So 0.104 liters. Any questions about this so far? Tell me what you get as an answer. .98 or 0.981, okay? And then the units, we can call it M or we can call it moles per liter. Either one of these is correct. I'm gonna just put that over here. This is our molarity. The last one we're gonna look for is molality. So it's a little m. And this is the same, very similar concept. So 0.102 on top, right? moles of solute. This time it's divided by kilograms of my solvent. And we have that as well. That's 100 grams of water, right? I must change that into kilograms. So it just becomes 0.1 kilograms. And tell me what you get. Okay, you get 1.02 molal. You can keep it as M, or you can keep it as moles over kilograms. So all three of these units are the same thing. Any questions so far?
I have a question, Professor.
Sure.
I did the molality by using density. Was that just like an overkill or?
It's not an
'cause I got a
overkill.
different answer.
You got a completely different answer?
I got 0.93. I mean, it's around the same ballpark. I know
That-
molarity and
That's
molality.
not
are
around the same ballpark. The reason why is because if you notice here, we didn't mention the well, we did mention the density of the solution, but again, these are numbers that we plugged in. So I would double check your calculation if you did it the right way.
Okay,
What you did is you told me 0.93, right?
for molality.
Yeah, try flipping it the
Yeah.
other way. Maybe this will increase to that. You might have flipped the scenario.
Okay,
Okay.
thank you.
All right. Is everyone okay if I erase everything on the screen here? Anyone still copying? Okay. All right, so let's continue. So now we're going to move on to the next part. This is called colligative properties. Okay. Number one thing you need to know about colligative properties. It is based on the number of solute particles, not what we have, but how much of it we have. Okay. So the more solid particles we have, the more effective the colligative property is. So we have a term called electrolyte. How many of you have heard of electrolytes? You hear it all the time. They mention like you should have good electrolytes, Gatorade, all these kind of things. So electrolytes is just another way of saying different ions, positive and negative. So a lot of the salts that you have, potassium, sodium, even chlorine there. So it's your way of saying, you know, the positive charges and negative charges. So the different ions, okay? You have two scenarios. You have a strong electrolyte and a non-electrolyte. Non-electrolyte does not dissociate into things. Things such as sugar, when you dissolve in water, it's still one sugar molecule. Things such as salt, if you dissolve salt, it becomes sodium and chlorine. It separates into ions. Those are electrolytes. So with that said, the stronger the electrolyte, the more solid particles, so the more ions it breaks into, the more effective it is. Okay. So we can see an example here. A strong electrolyte will generate electricity. A weak electrolyte generates a little electricity. A non-electrolyte generates no electricity. So how many of you have always seen that famous scene where there's water on the floor, there's an electrical wire touching the floor. If you step in the water, you will electrocute yourself. Like a famous movie scene, famous warnings, things like that. What if I told you the truth that the water itself does not conduct electricity? If you have pure water, it will not conduct electricity. It depends on the type of water that you have and what's in the water, okay? How many of you have also seen that famous thing where when you're trying to kill someone, they throw a hairdryer that's plugged in into the bathtub with the person in it? That's also a scenario. To clarify what that does, in the water, right? In regular water itself, if you just have water and electricity, it does not conduct electricity. However, what's in most of our water? It's not just pure water. Well, it's not necessarily hard water, it's ions, right? You have chlorine in our water in New York City. You have other minerals that are present. Those things conduct electricity. Now, if you step into the water, the ions on your body, so different chemicals that come off your body, those ions also affect the water. So just because you have pure water and you jump in there and you throw a hairdryer in doesn't mean you're safe. And the reason why is because you have ions on your body. Okay. So with the disclaimer, don't try it at home. But yes, you can never have enough pure water. If you were to stick this in, if you look at the picture of the non-electrolyte, this is just in plain water. No electricity is being conducted between the two because there's no ions being flown. In the middle here, it's probably a weak solution, as in they have a little bit of sugar and water. In the left picture, this is just salt and water, or something with a lot of strong electrolytes, so lots of ions present. Okay, any questions? All right. So the first, yes, so Dasani does have sodium chloride in it. A lot of your smart waters out there, so smart water brands, Gatorade, vitamin water, all these things, they just contain a lot of electrolytes. So sugar, salt, these are all mixed into it, and they actually upcharge you for it. So for the price of smart water, price of vitamin water, a little bit of salt, a little bit of sugar, you charge $2 to $3 for a bottle. So they're essentially selling you water at an upcharge price. So I can tell you, my old chemistry professor said something. If you can find another way to sell water and air, you essentially have found gold. So if you look at our everyday environment, like I said, Vitamin Water is one of these companies. Smart Water is another company. It's actually tied in with Vitamin Water. You also have things such as canned air. So there's canned air that you use to go ahead and spray laptops. They essentially packed air. They add other chemicals in there, like bitterant, so you don't inhale it. But they are selling you air and they are selling you water, things that you can find naturally. Okay, so our first colligative property, vapor pressure lowering. Anytime we have a solution, the vapor pressure of that solution is always lower than the pure solvent. So if I have water and I have salt water, the salt water's vapor pressure is always going to be lower than the water. So I want you to go ahead and write that down if you need to. We have two formulas here. We're going to go ahead. They mean pretty much the same thing. They both solve the same thing. It just depends on what you're looking at. Okay. So in your textbook, they may have this part a little bit differently, but when you see the P0, they may write it as solution. This just simply means your pure solvent. So the solvent that has nothing else in it, this is the vapor pressure of that solvent. This P solution here refers to the vapor pressure of your solution. So once again, I want you to make sure you are familiar with these two terms. And this middle piece right here, this is the mole fraction of your solvent. Now, what do we know about mole fractions? What is one thing we know about every mole fraction, no matter how many I have, even if I have 2 or more?
They all
What
equal
number?
to 1.
They all equal to 1 when I add them together. But what does that mean about them individually? Can any one of them be greater than 1?
No.
No, right? Can any one of them even be 1? No, right? They're always less than 1. Okay? The highest it can be is probably 0.99, assuming I have another fraction. That fraction always takes up a small percentage of it. If the two of them added together equals 1, the highest one of them can be is 0.99, and the other ones could be 0.01, for example. So with that said, any number I have here, the highest this can be is 0.99, which is right all the 9s across. Multiply by a number here. I'll say this is 100. This number right here on the left must always be less than 100. So the highest this could be would be like 99. Does that make sense?
Yes.
Okay,
Wait, I have a question, Professor.
sure.
So, for the first equation, oh well, both of them, I guess. So, the X solvent times the P solvent, right?
Mhm.
They both can't be 1, right?
So this can be any number. It depends on the pressure. This right here can never be 1. This right here can never be 1, if that's what you're referring to.
Wait, so the first two variables in the equation, not the solvent thing at the end.
I'm gonna just circle the 2 things that can never be 1. These 2.
Oh, I
items.
see. Okay. Yeah. Okay. Thank you.
Any mole fraction can never be 1. Always less than 1. Okay. Okay, let me just clear the screen so it makes it a little neater. Any questions about that first equation? Okay. If you look here, this refers to delta P. What does delta mean? Anybody remember? It means change, right? Also known as difference. Okay, change and difference. So this delta P here is simply your P solvent minus your P solution. That's what this means here. Okay, it's how much it is changing by. So this is your before and this is your after. The difference between these two numbers, that's what your delta P is. Any questions so far?
Can you please repeat that one more time?
The delta P is just the difference between these two boxes that I have circled. P solvent minus P solution is the change in the pressure. Any questions so far? Okay. To calculate P solvent, if I said what to make up a number here, let's say this is 0.75. Okay. So if this is 0.75, I'll assign the pressure for this to be 100. Just an easy number we can work with. 0.75 times 100, P solution should come out to 75. Does that make sense? All right. So 100 minus 75, what is my change? 25, okay? I'm gonna put that to the side, keep that in mind. If I only have this solute and this solvent, this is 0.75. What should my X solute be, or my mole fraction of solute be? 0.25, right? The two of these added together should always equal 1. My P solvent is the same. This is still 100. So if this is 0.25, 0.25 times 100 gives me 25. Does everyone see that? So these two equations are directly related to each other. Depends on what you're looking for. If you're looking for the change, it would be 25. If you're looking for the pressure of the new solution, it would be 75. It has changed by 25. Okay, so let's continue. We're going to skip this problem really quickly just because we did something very similar to it. If you want to practice this on your own, I'll leave this up for a few seconds and I'll show you the answers right after. You can scroll back to this part in the recording later, okay? But it's a very similar method. In this scenario, they want you to find the delta P, so the change first. Once you find the change, you can find the actual new pressure. Okay, the only difference here is that they're giving you information based in density here. So you need to do something with that density because you want to find mole fractions. They give you volume and they give you density. So you need to convert that into mass. Once you convert it to mass, you can then convert it into moles. So they're giving you extra steps along the way, essentially. So really quickly, you take the volume, you multiply it by the density that you get, you end up with your mass. You take the mass, divide it by the molar mass, you get the moles. So they just set it up for both of these here, for your glycerol and for your H2O. Now that you have the 2 moles, you also need to find mole fraction. Okay, so I'll leave this here for a few more seconds, and then we'll jump over and look at the mole fraction. So it does involve additional calculations. They're not always just going to give you the pure solvent and then the mole fraction and say solve it. Okay, now that you have this, you go ahead and find the mole fraction. In this case, they want the mole fraction of glycerol, which is of your solutes. If we look for the mole fraction of water, that would be our solvent. And we end up with this number right here, very small number. We assume that the other number, which is your mole fraction of your solvent, would be 0.994 or 502, whatever that number is, okay? You plug it into that equation that you see at the bottom there. The change is equal to this mole fraction of your solute times your pure solvent. And this is how much it is changing by. If I asked you to find the P solution now, right? At this point, you would simply just take this number right here, subtract it from this number. So these two numbers subtracted will give you P solution. What you started with, how much it is changed by, and what you end up with.
Professor,
Any
can you
questions?
read to the
Yes.
first, to the question?
Go back to the question.
Yeah.
Okay. This one.
Yeah, you're good.
Okay.
Thank you.
All right. Okay, so we've gotten to this part. The next thing I want to talk to you about is boiling point elevation. So boiling point elevation, really quickly, anytime you have a solution, it has a higher boiling point. Okay, that's the simplest way to remember it. If it's a higher boiling point compared to the original solvent. So if I take water and I add in some salt, the boiling point goes up. You can use the equation down here. This delta T is just simply how much the temperature has changed by. It doesn't tell us what the actual boiling point is. K is a constant. We will talk about what that constant is in a second. M is molality. Okay. So K is a constant. It's different for every single substance that we are looking at. Every substance has a KB and a KF. And since you heard the word KF, you can tell that there's also a freezing point involved here. So this is boiling point elevation. The next one we're going to talk about is freezing point depression. So how many of you see salt on the ground whenever it's snowing? People throw salt on the ground, right? The reason why they do that is because the salt mixed with the water actually lowers our freezing point. So if the temperature outside is 32 degrees Fahrenheit, that is the temperature at which the snow on the floor would turn into ice, or the water on the floor would turn into ice, and then we would slip. If you put ice on the floor, or if you put salt on the floor, the salt will mix with the water, and that lowers the freezing point. So you need to have an even colder temperature in order for it to freeze. And if you can get the temperature below what the temperature is outside, you have just changed that back into water. So that is why we throw salt on the floor outside. It lowers the freezing point. So it requires an even colder temperature to freeze it. Same setup here. You have molality, you have your KF, which is your constant, and then you have the change. So the thing about the change, if I calculate this number and it comes out to, we'll just say 10.00, this doesn't mean that the temperature at which things freeze is 10. You're taking whatever the freezing point is, and then you're subtracting this number from it. So you're lowering it. In the previous scenario, whatever number you get here, you're adding it to the boiling point. So everything has a different boiling point, every substance. So you're adding that change to that boiling point. Okay. Best way to remember this, boiling point elevation, it goes up higher than the boiling point. Freezing point depression, it goes below the freezing point. Any questions?
I have a question, Professor.
Sure,
On Alex, they have a negative KFM.
that's
So
fine.
the section it's the same thing.
So negative KFM, remember, you can have this value right here is just the change, right? Let's say we are looking at water. 0 degrees Celsius is when it freezes, right? Whenever I have the change here, let's say this number was 27.2. I would take 0 minus 27.2. So my final answer in actual freezing point would be negative 27.2. Does that make sense?
Yes.
Okay. That's how they get a lot of the negatives, because they're dealing with water and 0 degrees Celsius. Okay. All right. So the example I give you, when we pour salt on icy roads, it will essentially lower the freezing point of the water around it. Also, in this case, the snow around it. So since the rest of this is still at the normal freezing point, it stays as ice. But here, it requires an even colder temperature in order to remain as a solid. And because you don't have the lower temperature, it has essentially turned into liquid. Any questions? Okay, jumping back into phase diagram. The original solvents right here for our water. Remember, we said we would lower the freezing point. So we lower that, and we'd also raise the boiling point. So we've essentially expanded on the category of the liquid. So the liquid, it stays as a liquid for a longer time and more conditions, essentially. Any questions up to this point? Okay, we have a few more things we're going to cover and then we'll end. So the reason why this is relevant, boiling point elevation and freezing point depression in any car. How many of you have seen that iconic moment where they had a car that's overheating, they poured water in? Okay, so they do that because they're trying to cool down the car because it's overheating. They can actually use a thing called a coolant. So a coolant is also known as antifreeze. So coolant and antifreeze are the same exact thing. Okay. This is a Ford car, yes. So once again, you're going to go ahead and pour in, it's not ethanol. It's actually ethylene glycol. So a lot of the antifreeze and coolants that you have right now is ethylene glycol, okay? And it's not sugar. So it does have a sweet taste to it, but it's poisonous. So that's some of the things that they were kind of worried about, okay? Water does cool it down a little bit, but it's not efficient enough. Because if something is boiling, right, at whatever boiling point of water, then it's steaming, right? You pour water in, you're essentially allowing the water to steam again. So at that point, it cools it down for a little bit, but it's not good enough. Now, what we're doing here is when we add antifreeze and coolant in the radiators, right? Antifreeze and coolant is the same thing. This is a mixture of ethylene glycol and water. You have a lot of it present so that it lowers the freezing point. So it takes a lot more colder temperatures to freeze it, and it raises the boiling point. It takes a lot more higher temperature in order to cause it to boil. So it does both functions. It lowers the freezing point and raises the boiling point. Any questions? Okay. So some things I want you to memorize just to make things easier. Write this down. The boiling point is 100 degrees Celsius. Melting point, also known as freezing point, is 0 degrees Celsius. The KB, which is a constant, is 0.512 for the boiling. KF, 1.86. So the same amount that you add in terms of your molality of a substance, it will essentially lower the freezing point more than it will raise the boiling point. Based on the ratios you see here, 0.512 and 1.86. In fact, it is 3 times more efficient at lowering the freezing point than it is at raising the boiling point. And this goes back to just requiring more energy to boil something. Right? Does anyone else still need more time with this slide? In most scenarios, whenever they give you a question like this, they should be providing you with the KB and KF. But for water, there is a chance that they will not provide it for you. So you want to memorize this and have that on hand. Plus, most cases when you're dealing with this stuff, you will be working with water. Okay, any questions? All right, let's continue. I guess based on the time right now, we will end here. So I want you to just copy this question down and try it out on your own, okay? As you are copying this down, I'm also gonna go ahead and give you the polls. And I wanna talk to you about one thing, okay? So go ahead and work on the polls for now. Oh, it's not letting me send the polls. Give me 1 second. So give me a second. Let me re-log into the website and see if that works. Okay, it is not working. So for the purpose of today, there is no poll. Okay, we'll skip past that. Really quickly, the last thing I want to talk to you about. If you are celebrating or observing a religious holiday for the 21st and the 28th and that is why you can't take your quiz. I was told by the other recitation instructors that you guys also observe it on Wednesday, or I'm not sure if it's Monday, Tuesday, and Wednesday, or if it's Tuesday and Wednesday. So for the purpose of that, I'm going to make your quiz scheduled for Thursday. Go ahead and send me an email if that is you, okay? And send me a preferred time. I will decide on one time for everyone on Thursday, okay? Now, in
Wait.
addition to that, yes.
I thought the sample quiz was on Friday.
So to clarify, I'm not referring to the sample quiz right now. I'm referring to your actual scheduled quiz. Now, those in the Tuesday class, they're observing their religious holidays, so they can't take it that day. So I'm scheduling an alternate day for every one of those individuals. So if you're not in the Tuesday class and you're not observing a religious holiday, this doesn't apply to you. Okay, you take your quiz at the normal time. Don't worry about it. Okay. One other thing I want to bring up on the 28th. Does someone have a
Professor,
question?
yeah,
go
I'm a
ahead.
little bit confused. So we have a quiz, isn't it on the 24th?
So the 24th is for the Friday class, right? You're in the Friday class?
Yeah,
You don't have to worry about it. This is referring
Okay.
to the Tuesday class.
okay.
Okay. So once again, if you're in the Tuesday class and you're observing your religious holiday and you can't take the quiz that day, I am
Oh.
creating an alternate day for Thursday of that same week that you are taking it.
You're saying the Tuesday recitation.
Yes.
Okay,
Okay. Now, once again, send me an email if that is you, okay? Even if you send me one before, from this moment forward, so after 6:25, send me an email. Tell me the time that you prefer on Thursday. I'm going to go with the majority of it. Then I will let everyone know that is going to be the time. The time will be the same for both days. So both weeks of the 21st and the 28th, okay? Last thing I want to bring up, on the 28th itself, there is a chance that I have to attend a meeting. They haven't told me what time the meeting is. So if that meeting happens to fall and cut into a little bit of our time, if it's only a little bit of our time, we will still have class. We'll just end a little early or start a little later, whatever the two is, okay? Worst case scenario, if it's exactly when we have class and it covers the whole time, that's the only day we will do an asynchronous day. I will let you know in advance. I will have it recorded and we'll go forward from there. Once again, that is for the 28th. Okay, any questions? Recordings are posted. I have a link on your announcements. They go into a Google Drive, so it's just a link there. You just click on it. It's shared with anyone who has a link. So far, I only have that first one posted. It takes me quite a few days to post it just because it takes time to format it, sort through it, and then uploading it onto the website. Okay, anyone else have any questions? Once again, if you haven't done so yet, copy down the question on the screen here. I'll give you another minute or two for it, okay? There is no poll for today. For whatever reason, it wasn't working. Alex is due next week. Alex is not due this week. We just finished chapter 12. It should be due next week. I'll take another look at it in case there was an error, but generally speaking, I remember I said it to be due next week. Can someone confirm that?
yeah, it says on the,
Okay, so it should be due next week. Okay, once again, same strict rules. I am not giving any extensions. It has been 2 weeks since we started. You should have used the courtesy access in the beginning. Everything is still due at their scheduled time. You can't find the first recording. I'll take a look on my end. It was just that Google Drive link. Do you know where that Google Drive link is? Did you find that? Or you can't find that part? Okay, go into Blackboard and look at the announcements. It should be there. Okay.
so when you post the recordings, you'll send an announcement with the link?
Generally speaking, I'm not going to send individual announcements again because I have just posted it on the shared folder.